Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so far we have done in a very elaborate fashion the hydrogen atom problem in spherical polar coordinates, doing separation of variables, and we tried to solve it elaborately and looking at differential equation how it looks like the familiar special functions equation. Now we want to slightly go into a way which is applicable to all the central force problems. What is a central force problem? The potential energy is dependent only on the radial coordinate. So suppose your potential energy is dependent only on the radial coordinate, what happens under rotations? That's why it's called central force problems. They are rotationally invariant systems, right? So whenever we have a rotationally invariant systems, you can start seeing what is the corresponding operation, like translation. Translationally invariant system means what is the corresponding operator? Suppose you want to take a function f of x plus epsilon. This is translation. I can write as a Taylor series, right? Is that correct? An infinitesimal translation can be written for any function this way. But now I can rewrite this as f of x plus epsilon. Del by del x I will try to write it as a px operator. Okay. What do you have to do? Minus I by h cross can I put? For an infinitesimal one. If it is not infinitesimal, you can continue the series. There is no minus. Okay, good. Yeah, the minus I h cross del by del x is px. So if you want to write del by del x, then you can do this. Good. So for an infinitesimal translation, you have the corresponding differential operation is del by del x, which can be interpreted as if it is a momentum operator. So now I will ask you the next question. If I take an r vector and do an infinitesimal rotation, a rotation operator. What is a rotation operator? Let's take the rotation to be rotation by a small angle about z axis. What will that be? Is cos delta theta, let me call, sin delta theta minus sin delta theta cos delta theta 0, 0, 0, 0, 1. Can I do this? For an infinitesimal. So what is r? For delta theta small, keeping only linear term in delta theta, this can be written as someone 1 delta theta 0 minus delta theta 0, sorry 1, 0, 0, 0, 1, right? Can I do this? So what is this? It is f of r vector plus this off diagonal matrix. You could perhaps write it as some delta theta cross r vector. Check it out. I am doing this for a rotation about z axis. Just for, so let us keep this rotation about z axis and put this theta also with about z axis. You understand what I mean? If you do a Taylor series expansion, the first term will be f of r. The second term can be written as, this I want you to do yourself, but just you can yourself try and fiddle around and see what the second operation can be written as, and you will see there will be a angular momentum operator. you will see that it will be like f of r plus delta theta z Lz on f of r. Leave it you to check. I'm not going to do it right now, but so basically I am trying to drive the point that a translation can be for the wave functions also. Away by infinitesimal translation, if you want to achieve, you need a linear momentum. If you need an infinitesimal rotation, you need an angular momentum. If you do a rotation about z axis, you need the z component of the angular momentum. So, angular momentum is conserved in rotationally invariant system is what you have all learnt in classical mechanics, right? How did you check that the angular momentum is conserved in rotationally invariant system? Take Kepler problem or anything, Kepler system, central force potentials. How do you show that dl by dt is 0? The Heisenberg's equations of motion, which you do, which shows that the Hamiltonian Poisson bracket, right? Poisson bracket of any component, was that 0 for rotationally invariant system or central force. But in quantum mechanics, what do you have to do? This will become 1 by IH cross. Is that right? So, hydrogen atom problem is a central force problem which is rotationally invariant, and we expect the left hand side to be 0, and that is possible if Hamiltonian commutes with angular momentum, correct? They are compatible operators. So, this means hydrogen atom problem, all central force includes all V of R potentials, need not be just hydrogen atom. Rotationally invariant systems, angular momentum is conserved. In classical mechanics, Ehrenfest's theorem says that the rate of change of expectation value of angular momentum is conserved, and using your Heisenberg's picture equations of motion or Schrodinger picture on the expectation values. So, this is not a right thing, so I need to put an expectation value here, okay. If you say that the states do not evolve in time in Heisenberg picture, I can remove that expectation value, it is not required. I can write an operator equation. Everybody is familiar with this, right? So, this is when I am looking at Schrodinger picture, but I could write it in the Heisenberg picture as an operator equation. This is Heisenberg picture. So, all central force problems, angular momentum commutes with Hamiltonian. How do we see this in the hydrogen atom problem? We have done the psi NLM, but we never looked at it from this point of view, and that is why I was bringing in this angular momentum operator. Okay, so let me just briefly tell you the angular momentum operator and how angular momentum operator commutes with the hydrogen atom Hamiltonian. L dot L is what we call it as Lx squared plus Ly squared plus Lz squared. In order to study spherically symmetric systems, we use this r theta phi, and you can make a change of variable and rewrite all these Cartesian components in terms of spherical coordinates. What is Lz in spherical coordinates? And you can show that Lx, please check this, just a change of variable, write this as r cross p x component, rewrite it in terms of theta phi, similarly Ly, and Lz will be a minus IH cross del by del phi. So, it is just del by del phi. It is going to operate on which part of the wave function? Only the phi dependent piece, which is like e to the IML phi. L squared is also formally, you can try to write Lx squared plus Ly squared plus Lz squared, you combine this, and I will leave it you to verify this, okay. Why am I doing this? My aim is to show that the Hamiltonian commutes with, let's say, Lz, Hamiltonian commutes with L dot L. If it commutes with Lz, it better commute with L dot L also. Each Li it is going to commute. So how do we do this? So this is the differential operator position representation for the angular momentum, Z component and the L dot L. Now it's for you to check. If you take Lz on the hydrogen atom wave function, I already pointed out that it is going to be on the phi dependent piece of the wave function, which is roughly e to the I ml phi. So it will give you del by del phi, there is an IH cross here. So you will get ml h cross. So what are we seeing? We find that hydrogen atom wave function is an eigenfunction of the Lz operator. Is that expected? Compatible operators if you have should be the wave function solutions. If you have two operators A and B, the eigenfunctions of A and B will be simultaneous eigenfunctions. These were eigenfunctions of the Hamiltonian. We explicitly see that, I don't know whether you all see the thrill, that rotationally invariant system, Hamiltonian has to commute with angular momentum components. That means if it commutes, you can write a simultaneous eigenbasis for both the Hamiltonian and Lz, and it is happening. This is an eigenvalue equation. What is the eigenvalue? Eigenvalue is ml h cross. What about L dot L? This also you can see that this will be the operator form for your theta phi part of the wave function. Please go back and look at the theta phi part of the wave function, and you can see that you can pull out an eigenvalue which is not L squared but L into L plus 1 times h cross. Will you go and look at that theta part of the wave function? So you will see that, so L squared operator on your omega of theta phi, so this operator is exactly like the differential operator which was in front of this omega of theta phi, and you can show that it is C, which was L into L plus 1 times h cross square on omega of theta phi. Why only theta and phi are affected? Angular momentum, when you write the differential operator position basis, you see it's only on the theta phi. The theta phi. So your wave function, when you write psi r theta phi, you could write it as r of r omega of theta phi, and then when you try to write the differential operator, that differential operator is nothing but your L dot L operator. You can check that out. We wrote that differential operator explicitly there, but please you can go and check that differential operator which we have, which involves sine theta, del by del theta. So that operator can be written in a compact fashion as L dot L operator, and this one was from the differential equation that we compared it to the spherical harmonics, and we found that the solution is L into L plus 1. Okay. There is a h cross squared coming up here because of the definition of the L square. So please check this, L into L plus. So what is this? This is also an eigenvalue equation. Putting an R of R does not matter. Does it matter? So L squared on psi r theta phi is NLM is L into L plus 1 h cross squared psi NLM r theta phi. So the eigenvalue of the energy eigenfunctions for the L squared operator is going to be L into L plus 1 h cross squared. That's what at least we see from the hydrogen atom. Okay, with this data, couple of things which you can start attempting is orbital magnetic dipole moment. Sure, you all know this, right? Bohr magneton multiplied by the orbital angular momentum is the magnetic moment, right? This is the Bohr magneton. L is the angular momentum. Suppose I take the z component of this magnetic dipole moment operator, act on this wave function, it will be an eigenstate or not an eigenstate? Going to be an eigenstate, going to give you H cross cancels, you have a minus ml mu b, and similarly the magnitude of the mu vector, you can do mu dot mu. If you do mu dot mu, it will be L dot L. L dot L on the state is L into L plus 1 H cross squared. If you want the magnitude, it is not just L, it is the square root of L into L plus 1. Suppose you have a function of this L operator, they will also be eigenstates. That is all I am trying to say. So, where we have used LZ is this and L squared is L into L plus 1 H cross squared. And also you could remember that this is what I was saying, this operator which I have is your L squared operator on omega, and C was L into L plus 1. So, why am I slowly going into this? Typically, we will have interacting with the magnetic field. What is that effect called? Zeeman effect. So, what will be the term in the potential energy you have to add? Mu dot B. If you turn on a magnetic field and if the object has magnetic moment, orbital magnetic moment, there will be a mu dot. So, what is our aim? If we add this term, what happens? Experimentally, you all know what happens. What happens? There is a splitting, right? They start seeing that some of the levels which are degenerate, they separate. Right? This is what they saw. Can we see this from equations? Okay. So, we try and operate this operator. Hamiltonian will be, let us take mu dot B, or the hydrogen atom Hamiltonian added with a minus mu dot B. When we turn on the magnetic field on a central potential, you had the hydrogen atom Hamiltonian and then a minus mu dot B added to it. So, we know that the hydrogen atom will give you a En energy, but this interaction term or this potential energy due to the magnetic field, we have done this. What does mu z do? If suppose you take the magnetic field to be along the z direction, mu z will give you a ml times minus ml times mu b, right? We seen this. Sorry, I should have put a multiplying that wave function, which I have not done. So, please put that wave function. So, it is an eigenvalue equation again, but initially the energies of those wave functions were En. They will still be En only for ml equal to 0, but ml not equal to 0, it starts showing whether it is plus or minus L or it goes from minus L to plus L. There will be distinct levels with different energies, and that shift will be Bohr magneton times the magnetic field. Is the way of using eigenvalue equations, simultaneous eigenfunctions of commuting operators, everything comes into picture, right. So, this is one thing which you should see, but what exactly you have? Initially there was a degeneracy, but now 2L plus 1 states for a given L have different energies. So, I said that the Hamiltonian commutes with Li equal to 0, where Li could be Lx, Ly, Lz, but for convenience Lz operator was minus IH cross del by del phi, and we found that H and Lz is 0. This is fine. Suppose you take the Hamiltonian, which is p squared over 2m plus v of r, and then I want to also add a mu dot b, and I take the mu to be along z direction. So, then what happens here? It is p squared over 2m plus v of r, and then this will be a Bohr magneton times Lz quantum number times Bz. Okay. So, let me not write those factors, it depends on Lz operator. Now the question you are asking is whether this new Hamiltonian, this is a new Hamiltonian, whether it commutes with Lz. It doesn't commute with Lx and Ly. The old Hamiltonian commuted with Lx and Ly also. But the new Hamiltonian commutes still with Lz. Is that obvious from here? Adding a term proportional to Lz, if I take the commutator with Lz, this term anyway commutes and this will also commute, trivial. So it is a simultaneous eigenstate of Lz and Hamilton. So if you go and write your wave function, write it this way. You will see that that shift will shift the energy by an overall ml factor. And that keeps adding to your energy eigenvalue. So whatever you found En will get an ml mu That's what will happen. I am arguing from a different point of view that a Hamiltonian, initial Hamiltonian of hydrogen atom commutes with Lz, but I can also write hydrogen atom plus a mu dot B with the mu z Bz Lz, that is also 0. From here also I can find what is the shift in the energy by using the operator formalism. Even from the wave function formalism, you will see that there will be a shift. So what is happening is that this one was having a n square degeneracy. Now you will see that will get, for a specific L, there will be a splitting which is happening, and each one will be this difference will be a mu bb, 2 mu bb and so on. You understand what I am saying, right? That is the Zeeman splitting. Okay, so I am just trying to say that you can formally do this also and check out that the shifts in the energy happens. It is no longer degenerate. There will be a 2L plus 1 states for any given L having different energies, and so the degeneracy gets lifted by this Zeeman effect. L equal to 0, what is expected? Will there be this effect? So L equal to 0, in the presence of magnetic field or in the absence of magnetic field, I don't see any difference. L equal to 0 is like as if the particle is almost at rest. Doesn't have any, no, it's kind of heavy and stationary, or it is rest, that you can treat the state to be at L equal to 0, and the spectrum will not be able to say whether you are in B equal to 0 or B not equal to 0. Experimentally, this is not true. What do they see? There is this additional thing which we never brought in our Schrodinger equation, which is the spin angular momentum, and we cannot discuss spin angular momentum in non-relativistic Schrodinger equation. Non-relativistic because your kinetic energy operator is p squared over 2n. If you want to do relativistic quantum mechanics, what should be the modification? The kinetic energy or the total energy has to be written as p squared c squared plus m naught squared c power 4. This is the way you have to write in the square root, right? So that's not what we are doing. We are always taking the kinetic energy as p squared over 2m, which is non-relativistic quantum mechanics, and we are studying non-relativistic quantum mechanics, which is the Schrodinger equation, and we cannot see this additional quantum number, which is the spin quantum number in non-relativistic quantum mechanics. But experimentalists are not governed by this. They are seeing what they are seeing. So they are saying even for L equal to 0, they see degeneracy is lifted. But mathematically I see L equal to 0, there is no distinguishing whether we put a magnetic field or no magnetic field. Clear? Okay, so that brings in the concept by putting by hand electron spin quantum number in non-relativistic quantum mechanics. So experimentally, when they do a transition from n equal to 3 to n equal to 2, they do see that there are small closed lines which are 0.114 nanometer apart. They cannot account it without introducing the electron spin quantum number. And also in the Zeeman effect, as I said, L equal to 0, they did see two lines. They cannot account for it just by mu dot B term, which is where mu is the orbital magnetic moment. And the other convincing thing is the Stern-Gerlach experiment, which involves a beam of silver atoms which are produced, and it's made to, they are taken to be almost at L equal to 0, and they are made to go through this inhomogeneous magnetic field, and they see two beams coming out. So these experimental results cannot be understood using Schrodinger equation. What is the reason? This I have already said. Schrodinger equation is applicable for non-relativistic particles, whereas electron spin is a relativistic effect. So for relativistic theory, we need to study Dirac's equation, and these people had proposed a spin quantum numbers which is same for all the electrons. So what does that tell us in theory? I have to introduce a similar term like the way we introduced the orbital magnetic moment, a spin magnetic moment, and we also introduce the proportionality factor, which is the G factor, and ms is taken to be plus or minus half. If we take this, then we can account for all the experimental data. Okay, so just like your orbital angular momentum L and azimuthal quantum number L and ml, you can have an S is always half for the electrons, and you will have an ms which goes from minus s to plus s. If it is half, then it goes from minus half to plus half. That's why you see two distinct lines which is accounting for the spin angular momentum even though L is 0. Even though L is 0, when you turn on a magnetic field, you see two distinct lines, two splittings, is because of the spin quantum number with s equal to half and ms equal to minus half and plus half. So let me stop here.